Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. Today I'm going to do example problem 13-8 from the Schwarzenbach et al. Textbook, the second edition. This is about the hydrolysis of an insecticide in a river. The insecticide here is this stuff called disulfoton. And you know, they like to give you these word problems, right? That they try to pretend are real. This might be real, I don't really know. So after a fire at a chemical storehouse in Switzerland, several tons of all kinds of horrible things were dumped into this nearby river, the Rhine River. And among these chemicals was the insecticide disulfoton, of which 3,500 kilograms were introduced into the river water. During 8 days of travel time from Schweizer Halle to the Dutch border, 2,500 kilograms of this compound were eliminated, i.e. they're missing. We don't know what happened to them. And somebody wants to know how much of this elimination was due to just regular abiotic hydrolysis, meaning just reaction with the water. And so you don't have any good data in the literature, so you have to go into the lab and do some measurements of your own down here. And then the question is, in the conditions in the river, which are 11 degrees Celsius at a pH of 7.5, how much of the disulfoton was transformed by hydrolysis versus other mechanisms, okay? So the reason that you're doing a couple of measurements of the K observed at these really high pHs, almost to pH 12, is because you want to know whether the base catalyzed mechanism is important, right? So that's the first question. Is the base catalyzed mechanism important, or is it just the neutral mechanism? And they were basically trying to do the same pH for these two. It's just that, you know, you can't always control your pH really accurately. So the pH in the one experiment was 11.98, and the pH in the second experiment was 11.72. But really, they were trying to do the same pH at two different temperatures. So they're trying to see what is the change in the rate constant over a 10-degree span for the base catalyzed mechanism. They did 4 measurements for the neutral mechanism, but they were, you know, kind of thinking maybe the base is not as important, so they only did 2 measurements for the base catalyzed mechanism. And you can see that the rate constant went from 3.6 times 10 to the minus 5 to 1.3 times 10 to the minus 5. So it dropped by more than a factor of 2, almost a factor of 3, over a span of 10 degrees Celsius. So that tells you that the activation energy is substantial. It's not nothing. And here, so going from 40 to 30 degrees C for the neutral mechanism, you drop by more than half, 9.6 down to 4. So similar orders of magnitude. You drop by more than half here, and you drop by more than half here. So the activation energy, I mean, just without doing a bunch of calculations, the activation energy is similar for the base catalyzed and the neutral mechanism. So if we look at this first, let's do 30 degrees C here. Okay, so this is K observed, which has units of 1 over seconds, because it's a pseudo first order rate constant. And this is at pH, this was 11.72, and that'd be a pH. And then temperature was at 30 degrees Celsius. Okay, so at this temperature and pH, first of all, the OH concentration would be what? It would be equals 10 to the 14 minus 11.72. That can't be right. Sorry, this is the OH concentration, right, which would be just 10 to the, 11.42 minus 14. That's what I did wrong. I got my signs wrong. Here we go. Okay, so that's the OH concentration, and this is in units of molar. You should always keep track of your units, okay? So that's the OH concentration at a pH of 11.72. Okay, so then if I want to convert this K observed, this pseudo first order rate constant, into a second order rate constant, I need to divide it by the concentration of the OH, right? So then K, we'll just call this K second order, is equal to this K per second divided by the molarity of the OH. And so now this has units of 1 over molar seconds. Okay, so now this is a second order rate constant for the base catalyzed reaction. And it's 6.86 times 10 to the minus 3. Okay, now the question is, what would this reaction be? What would the rate of that reaction be if we were at a pH of 7.5, which is what's prevailing in the water column, okay? So K, I'm going to call this K prime because that's what you always call pseudo first order rate constants, whatever. So this is at pH of 7.5. So before we do that, let's calculate our OH concentration. Fucking has math. OH minus brackets in molar. This was here, this was pH 11.72. And now we're at, see, it just changes the case on me, pH 7.5. So here it is now equal to 10 to the 14 minus 7.5, right? That's not right. I can do math, I really can. I made the same mistake again here. 17.5. 7.5 minus 14, is that right? 10 to the minus 7, yeah, that's right. That's the concentration of OH at pH 7.5. Okay, so then I multiply that times our second order rate constant here, which is in per molar second. And now I'm back to another pseudo first order rate constant of 1 over seconds, but now this is at pH 7.5. And we're still at 30 degrees C. So that's important to keep in mind. We haven't adjusted anything for temperature. We're at 30 degrees C. But notice, our K observed is now 2 times 10 to the minus 9, okay? And the actual conditions in the river are 11 degrees C, so that's only going to go down, right? So we're going to compare that to the neutral at the same pH, or close to the same pH, 4.0 times 10 to the minus 7. It's probably not going to be important. It's more than a factor of 100 slower. So in other words, we could probably ignore the base catalyzed mechanism, okay? We'll make extra sure of that later, but for now, let's just say we can ignore it. Okay, so here's our data. So now what we want to do, all of that was to determine whether we could ignore the base catalyzed mechanism, right? That was the whole point of what we just did, of all those calculations, of this right here. The whole point was just to figure out roughly, just guesstimate, not guesstimate, but roughly what is the rate of this going to be at temperature, or at a pH of 7.5. Remember, so here's our rate constant at 7.5 and 30 degrees C. It's only going to go down from here, right? It's going to go down by almost 20 degrees because it's going to go down to 11 degrees. So it's going to go down by more than a factor of 2, probably close to a factor of 4, right? Because this already went down by more than a factor of 2 over just 10 degrees. So this is only going to get slower, okay? So now here we have our temperature and our K. And if we want to convert temperatures, we need to use this equation right here. And to use this equation, we need to know what the activation energy is, right? The activation energy we can figure out by plotting 1 over T. And of course, this has to be in Kelvin. Whenever you do 1 over T, it's got to be in Kelvin, because if it's in Celsius, all the signs get mixed up and you got negative numbers. It just doesn't make any sense. And then this is going to be log of the first order rate constant. Now notice, this is a first order rate constant because it's a neutral mechanism. So there really is no second order rate constant. We don't worry about the concentration of water, which is the nucleophile here. So the first order rate constant is the rate constant, right? We don't calculate a second order rate constant for the neutral mechanism. So this is equal to 1 over that degrees plus 273.15, because I like to be very precise. There we go. So there's our 1 over T, right? And here's our log of K. Booyah. All right. And now we plot these. This is sort of like the Clausius-Clapeyron equation that we've been doing all along. And yes, they're quite linear, right? We could add a trend line. And yep, R squared's 0.98. That's pretty good for lab work. I'd be happy with that. So let's calculate the slope directly. Slope equals slope y, which is log K, comma x, which is 1 over temperature. Boom, there's your slope. And just for completeness, we could calculate the intercept. Intercept y, comma x. And really, to be very complete, we'll do the R squared plus Q, Y, comma, x. Okay, just for kicks. Okay, so this is our slope. Our slope is equal to the activation energy over r. Okay, right, so this is another way of looking at it. We're like, this is y and this is x. So this is m. Y equals mx. So this is m. So our slope is EA over r. So this is equal to EA over r. And yeah, I know there's a problem with my formula. Yeah, no, I didn't actually want help. No, I don't want help. Go away. Okay. Put our little apostrophe here. That will make it all better. Okay, so that's our activation energy over r. Okay, and the slope, again, is rise over run, and the rise is the log k, which has units of 1 over seconds, and the run is 1 over t. And so if I want to convert this into an activation energy, I need to figure out my units of r. And if I want activation energy, I want r to be in units of something like joules per mole Kelvin, right? So 8.314 joules per mole K. And because this is the slope, it has to do with the run here, which is the temperature, which is 1 over T. So when we multiply, so we're going to take this slope and multiply it by R so that we get the activation energy, right? So EA is going to be equal to that slope, equal to the slope times R. Boom, okay? And so now, because this was already in 1 over K, now we're going to have units of joules per mole, right? So that's good. Don't worry about the sign. Signs are really not very important here in terms of activation energies and stuff. But this is in joules per mole, so sometimes we might want to divide it by 1,000 to get kilojoules per mole. And the reason I do that is just so I can kind of do a gut check. Does that make sense? 34 kilojoules per mole. That's actually on the low end. I would expect a lot of reaction rate constants to have higher activation energies than that, but it's acceptable. It's reasonable. It's in the ballpark. So that's cool. All right, so now I can use this equation to calculate my K, my rate constant, at my other temperature, which is now 11 degrees C. So temperature 2 is 11 C. Sorry, put it up here, 11 C, which is 273.15, which is 284.15 degrees Kelvin. And then temperature 1, well, we could do this a couple of different ways. Probably the easiest way is to just pick a temperature 1. And so we'll pick temperature 1 as the one that's closest to us, which is 30 degrees. So we'll pick 30. The one that's closest to what we're trying to figure out that we actually have data for, right? So that's 303.15 degrees Kelvin. And the K at temperature 1 is, we already have up here, it's 4 times 10 to the minus 7. Okay, so K at temperature 2 is equal to EA over R, which is actually the slope right here. We don't have to calculate it all special again. We've already got it. So it equals EA over R times T1, 1 over T1, sorry, 1 over T1 minus 1 over T2, parentheses. And then remember, when we take the natural log, we could write this as ln of K2 minus ln of K1. So then we could say ln of K2 and then move the minus ln of K1 over here. So it would be now plus ln. Oh, you know what? I just realized I made a mistake. But that's okay. I can fix it very easily. Okay, ln of K at T1. Boom. Found a typo. Sure, that looks good. Okay, so this is now our K at 11C. Now, let's ask ourselves, does this make any sense at all? And the answer is no. A couple of reasons. So first of all, why do I know that doesn't make any sense? Because it should be slower than it is at 30 degrees C. And look, it's 8 orders of magnitude higher than it should be. So what did we do wrong here? Well, first, we forgot to correct the sign here. This is negative, right? So I'm just going to put a negative sign here up here to negate that. The other thing we did is more subtle. I should have used natural log here, not base 10 log. There we go. now it makes more sense. So now our activation energy is 78 kilojoules per mole. That makes a lot more sense to me. Yay! Okay, so see, even I make mistakes, but the important point is to be able to catch them. So 78 kilojoules per mole makes a lot more sense to me. Okay, still, this is too small. What are we doing wrong here? Maybe we have a parentheses problem. Let's try to see if we can fix our parentheses. Does that work? Nope. Yep, this is way, way too fast. So now I'm going to pause the video and figure out what the heck I did wrong. Okay, after that brief interlude, I realized I didn't do anything wrong. The problem is not me. The problem is that this is not k. This is natural log of k. Duh. Okay, see? We all make mistakes. Okay, so the actual k then is 10, or it's actually exp of this, which is 4.9, or about 5 times 10 to the minus 8, which is just exactly what I would expect because it's quite a bit, well, not quite a bit, but, maybe a factor of 10 lower than what it was at 30 degrees C. That makes total sense to me. Yay! Oh, we got it. And it has units of 1 over seconds. Booyah! Okay, so units of 1 over seconds. Now, what happened to all the mass of this stuff? This what is it called again? Disulfoton. Where did it go? Okay, so we started out with, what did they say? 3,500 kilograms. And now 2,500 of them are gone. So C0, or it's actually mass 0, equals 3,500 kilograms. And mass at time 1 equals, it's actually, what did they say was gone? 2,500 was gone. Yeah, 2,500 kilograms of this compound have been eliminated, which means that only 1,000 are left. Right? Okay, so that's M1 over M0. And then if I find the form of the equation that lets me calculate concentrations, we can just use concentration or use mass instead of concentration. So let's go find that formula. That should be in the lecture notes on chemical reactions, right? All right. So here's the formula that we were looking for that tells us what concentration of our chemical, in this case they're calling it chemical A, we would expect at a given time, given that you start with concentration A at time 0 times e to the minus kt. Okay? Now we know what T is, right? T was 8 days of travel time. So T equals 8 days, right? So let's see. Multiply that by 24 hours in a day times 60 minutes an hour times 60 seconds per minute. That gives us that many seconds of travel time. Let's call it S, seconds for travel time. Okay, so A over A naught would be equal to e to the minus kt equals exp minus k, which we've already set up here, was, where's our k? K is here, minus k, times t, which is just above us there in seconds. Okay, so in other words, A over A naught is 0.966, meaning that 96.6% of our mass should be left. The reaction's pretty slow, so really not that much of it has gone anywhere. Right? This is 10 to the minus 8 per second, and we've only got 10 to the 6, 6 times 10 to the 6 seconds. So it's just not that many. So not that much has happened. We're expecting a loss of only 4%. So we expect a loss of about 3.4%, right? Right, we're expecting a loss of 1 minus this 0.966. Right, so yeah, 3.4%, okay? So did we have a loss of 3.4%? No, we had a much, much larger loss than that, okay? So M1 divided by M0 here is much bigger. We have a loss of 3.5 times. Let's see, sorry, let's do the M1 over M0, 3.5. Yeah, sorry, we have this backwards. M1 over M0. Yeah, so we lost, this is what's remaining. The loss was 72%, right? 1 minus this is how much was lost. So we lost 3/4 of the mass, but our reaction rates tell us that we should only have lost about 3% of the mass, right? So much more of it has disappeared than we can explain with, this abiotic reaction. And this is a good point to stop and ask ourselves, did we really have to worry about the base catalyzed reaction? Remember, here was our base catalyzed reaction constant at 30 degrees C, 2 times 10 to the minus 9. And here's what we calculated for the neutral mechanism, 4.8 times 10 to the 8th. So about a factor of 20 faster. And again, this is only going to get slower when we adjusted it down for temperature. So I think we are justified in ignoring the base catalyzed reaction. So the way that I did it in this video is slightly different from what I did in the file, which is over here. There's the fully baked cake, but it's the same general idea, and I think I've gotten essentially the same. Yeah, this is how much mass is remaining. This is how much should be remaining. I had a slightly different answer here, but roughly the same idea. So hopefully that will help you understand this problem, and let me know if you have questions.